Hello, Math 20-1. Welcome to absolute value equations. So if you remember from last day, we had learned about absolute value and writing them as piecewise graphs, And now we're going to take that to the next step. But remember, the big key thing of absolute value functions was that in order to write them as piecewise, that you had a positive case, which was just, if we remember our absolute value x, we had a positive case, which was simply just x if x was greater than or equal to 0. And then we had minus x if x was less than or equal to 0. And remember, that piecewise concept is what we're going to use to solve equations. In essence, in order to deal with absolute value functions in calculus, we need to rewrite absolute value functions in functions without the absolute value. So you need to rewrite them as piecewise. And the same thing is going to occur when we try to solve algebraically single absolute values. You need to rewrite them as piecewise. And that's going to be the essence to work with these algebraically. That piecewiseness is how we deal with these in, in calculus. But we also need to explain, well, why does the absolute value of f of x have no solution, okay? And we're going to look at some of the things we're going to talk about here. We'll talk about in class tomorrow. I'm going to emphasize some of the restrictions and so on, and that might seem a little confusing, and we'll talk about that more tomorrow. But I'm going to talk about everything that would be in a calculus class, and then we'll be more specific about it in class tomorrow when we work on our assignments, okay? But that's the nature of, of that important concept. That importance of piecewiseness is a really important thing for Math 31. Okay, so let's get at it. Here we go. Excuse me. So absolute value functions, some of the things we talked about last day. Really, really important. Positive part of it and the negative part of it, right? What do we know about it? Well, we know that the range has got to be, that the range of this, sorry, but that's a typo. The range of this must be greater than 0. So in other words, when you graph this, y must be greater than 0. When you guys go to your, to graph this on your graphing calculator, and if you wanted to type in y equals absolute value x, obviously you see the positive part of the graph and the negative part of the graph, but clearly the range is y such that y is greater than or equal to 0. You can't ever get a negative out of an absolute value, right? So if somebody asked you to solve, well, when is the absolute value of a number equal to 3? You could probably solve this intuitively, but let's just look at that situation and see, well, how would we do that? Well, case number 1 would be, come on, the output must not be negative. You can't get a negative, of course. To solve it, you'd write case 1, and I'm going to call this, as we always do, the positive case. When is it greater than 0? Well, when is the absolute value of x equal to x? The first equation would be x equals 3. How do you solve that? Well, x equals 3. What's the second equation? Well, the negative case of the second equation is obviously absolute value of x equals minus x. So then the equation would be minus x equals 3. Well, when does minus x equals 3? Obviously when x equals minus 3. Obviously very simple. So what are the two solutions for absolute value of x equal to 3? Well, clearly it's plus 3 and minus 3, because those are the two places where, where the absolute value of x is 3, or the distance is 3 units away from 0, right? Oh, you can't quite see this. How can you use the definition, the distance of 0, to determine solutions? Well, obviously, if you want to be 3 units away, you can either be 3 up or 3 down, right? How do we solve it graphically? Well, I want you to stuff this in your graphing calculator and see what you'd see. Well, if you stuff it in your graphing calculator, you could type in one equation as y equals absolute value x, and you're going to get the red graph. And you can try this on your calculator right now. Excuse me. And if you do, you'll see the red graph. When you type in the green graph, which would be y equals 3, you're going to get that green line. So where are the two answers? The two answers are the x values of the points of intersection. So you have two graphs. One of them is on the left side of the equation, one of them is right. We can call this one y1 and this one y2. And that's where you see where your points are. One of them is at +3, one of them is at -3, and there's your two answers. I want to show you another way that you could use your graphing calculator. So if I just end this show and I go to my graphing calculator for a second. Oops. We'll discard those, and we look at my graphing calculator and we say, hey, what if I was to graph, I don't want this one, but what if I was to graph, and notice what I did here. I took, and if you look at the equation that I have in my calculator, the absolute value of x minus 3. If I graph that one on my graphing calculator, and now I hit graph, you'll see, whoops, I want to zoom, standard, what you'll see is now instead of looking at two graphs, I took it all to one side, and I'll show you on the next page. I'll go back to the notes in a second. But if you take it all to one side, look back at the equation, what I did with that same question is I took everything to one side and went absolute value x minus 3. And now when I graph that, instead of looking at 2 points of intersection, you can see that my answers are the x-intercepts. So you're looking at where the graph equals 0. And sometimes that's easier. You'll see later on, maybe you like that better. So there's two options to solving graphically. And I'll turn my thing back on again. You can solve graphically this equation. Oopsie. You can solve that graphically by graphing y1 equal to absolute value x and y2 equal to 3. And then you look for the points or x values of the points of intersection. Okay. Another way to do this is, it's the way I like better, is I take it all to one side and I do this. Absolute value of x minus 3 equals 0. So instead of graphing two things, I go, oh, I'm just going to graph y1 equal to absolute value x minus 3. And if you remember what you saw a graph that looked like this, and my answers are the critical numbers, are the actual x-intercepts. So now when you graph this one, you look for the values of the x-intercepts. So whenever we solve things graphically, you have two options. You can take it all to one side equals 0 and look for x-intercepts are the solutions. And if you like that method better, great, do that one. And if you like the one that's on the PowerPoint, you can do that one too. Okay, so there's two ways to solve graphically. I'm not going to do it on every one. We can talk about that more tomorrow. Okay, next question, you go, oh, what am I going to do with this? I have absolute value of x minus 5 equals 2. So we're going to go to tougher and tougher questions. So how do we handle this? Once again, rewrite it as a piecewise function. What are the two options? You cannot have a negative output, which is good, okay? You know that you can't have that. Now there's two pieces, right? The positive piece is x minus 5 when x is greater than or equal to 5. The negative piece occurs, because remember your critical number is 5, the negative piece occurs if x is less than 5. Now, you might, this part we can talk more about tomorrow, but we did that in the last class, and that's kind of important. So, case 1 is the positive piece. Case 1 is, can you solve the question, and I'm just going to do this by hand, can you solve the question when x minus 5 equals 2? Well, solve that simple little equation. Pretty simple. Take the 5 to the other side, and I get an answer of x equals 7. Nice. That's the positive case. Positive case. Check that answer. That value of 7 is within this condition of x is greater than or equal to 5. So that makes you happy, because in this condition they were supposed to be greater than 5, and it is. That's good. Case number 2, the negative case. The negative case. Well, what's the negative case? That's when you have minus x minus 5, right? And if you have minus x minus 5, how would that be equal to 2? Just simply solve that question. You have to distribute the distribute the negative, right? So if you distribute the negative, you get well, in this case, what I did was I took the negative to the other side rather than put it in. You could do whatever you want, but you need to solve that little equation. So if you took the negative to the other side, multiplied both sides by -1, you get x minus 5 equals minus 2. When you take 5 to the other side, you get 3. That value of 3 is your answer. Is that within the restriction we have up there? It is, so that's a good thing. Now, the only thing you still have to do is you still are supposed to check your answer. You might say, well, why do I have to? Because you do. The roots of these equations are supposed to be 3 and 7, but we talked about extraneous roots before. We need to check that. These two cases are called the derived equations, but you still have to verify your answers to see if there's extraneous roots. So I plug in x equals 3. Does it work? Yes, it does. 2 equals 2. Nice. I check to see if 7 works, and it does. X equals 7 gives me 2 equals 2. Good. Both of these values work. That makes you happy. And then we can move on to our next question. Now, what Cal is saying, Mr. K's dog Cal is saying, is that to solve any absolute value equation, you need to solve two separate equations. What are they? They are simply solve the question where the case is positive and solve the question where the case is negative, and you're good to go. Okay? So we can look at this and say, well, what if I wanted to see the picture of this and see, does this actually work? You can look at this graphically and use technology. So again, you can graph it with these two functions and say y1 is the left side, y2, the green graph, is the right side. When I graph them, I see where the points of intersection are, and I can see that 3 is one answer and 7 is another. So this is another way to check it. Graphically, I can see that it's definitely 3 and 7 are the answers. Can an absolute value ever be equal to this? So look at this. Can this ever be true? Now, could you ever take the absolute value of something and equal a negative? No. So if somebody ever asked you a question like this, you would have to automatically say there's no solution, because you could never take the absolute value of something and get a negative. It's kind of like saying, when does x squared equal to minus 1? And that's not possible either. You could never square something and get negative 1. You could never take the absolute value of something negative. So there's no solution. The absolute value of something could never be negative. Okay, in our next situation, writing it in piecewise is something that I'm doing in each one of these. But in essence, you can get away with solving these without doing that. You still have to check your answers. So in every one of these questions, you have to start off by saying, what is my positive case and what is my negative case? This restriction over here, we can talk about that more tomorrow. That's what we did in the last one. But we could start by just simply going straight towards our cases. Before we do that, if you were doing calculus, they would ask you for the restrictions of everything in the equation. Why? And I'm going to ask you this. What is this restriction here for? So can you please answer me that tomorrow, okay? It's not really going to affect our work with the question a lot, but it is kind of important as you move forward in calculus. So let's talk about that tomorrow. Some of these ideas of restrictions. Now let's get to solving the equation. How do I solve this? Case 1. Case 1 is the positive case. So remember, simply take positive 3x plus 2 and make it equal to 4x plus 5. Solve it. Done. X equals minus 3. I wonder if that actually works. Okay. We'll find out because we'll check it. Case number 2 is we will take this negative case and make it equal to 4x plus 5, right? So in case number 2, you solve that. Now you've got what you think are your two answers. Now notice, based on restrictions, and I want us to talk about this tomorrow, but I'm going to leave that till tomorrow. For you, what you need to do really now is I want you to make sure these answers work. You always have to check them, just like Cal the dog said in the last page. So does x equals minus 3 actually work? And you'll find out it doesn't. That answer doesn't work. And you might wonder why. Well, we're going to talk more about that tomorrow. If you check x equals minus 1, you'll find that it does work. Calculus makes sense. And why that answer works has to do with understanding the fact that that x equals minus 3 never had a chance of working. Even before you checked it, you knew it wasn't going to work. So we'll talk about that more tomorrow, okay? In essence, the main part of what you need to be able to do is solve the positive case, solve the negative case, Every absolute value question just creates two equations that you have to solve, and they're good to go, okay? The solution to this question is only -1. That's the only answer that worked, okay? Again, we'll go to solving with your graphing calculator, right? So you can graph one graph, graph the other graph, and the only place that these two graphs intersect is at -1, so you can see it visually. You can also do it the other way, and I'm just going to go back to my calculator to show what it would look like. So remember we talked, the other way to solve this question is take it all to one side and see it graphically. Y1 equals absolute value 3x plus 2 minus 4x minus 5. And if you take it all to one side, now you're just looking for x-intercepts. So when you look at what this looks like on your graphing calculator, you end up with a picture like this. And then once again, same thing, whoopsie, same thing when you look at that, you can see that it only has one x-intercept at x equals -1. So either way, you can solve these things graphically. Sometimes it's just easier to see x-intercepts. The last algebraic question, and I want you to try and fly on your own. Again, you simply start off with the positive case and the negative case, all right? So the positive case would simply be case 1. We'll talk more about the restrictions, but simply the positive case, this part here, I want us to talk more tomorrow, but we're not going to talk much about that now. Simply do case 1 positive. X squared minus x minus 12 is equal to 8 minus 2x. Solve that. It's a quad equation. You guys have solved that before. Take it all to one side, factor it. X equals 4, x equals -5. I wonder if those answers work. You're going to have to check them after, okay? We can talk about the domain, do they fit within there, but mainly just verify them. If you plug in 4, excuse me, does it work? 0 equals 0, it works. If you plug in -5, does it work? Awesome. So those two answers should be good to go. But you're not done because you have the negative case to do as well. So negative x squared minus x minus 12 equals 8 minus 2x. Another quad equation. Excuse me, take it all to one side and solve, and you get 4 and -1, two more answers. And so now we check and verify, do those answers work? And you'll find that x equals 4 does work. Have we created any new answers from the previous one? No, but that 4 came up again. And this really has to do with who does 4 belong to? Does 4 belong to the positive case or the negative? And we had that chat in class. In essence, 4 can belong to either one because at that point it's 0, okay? If you graph this, whoopsie, so what are our answers then? Well, our answers are, as we said, 4, 5, right? 4, 5, and -1, okay? They all worked. If you want to solve this graphically, again, you put in your graphing calculator and you will see that these two graphs intersect at 3 different x values, -5, -1, and +4, okay? So graphically you can see them, and you could have graphed it the other way too. All right, lastly, some applications, right? Before a bottle of water can be sold, it can be filled 500 meters plus or minus. What's the minimum maximum? Kind of a common sense question that I'm sure you'd be able to do, but one way to solve it would be, if you wanted to make a formula, would be the total volume minus 500 is equal to 5. So the difference between the volume and 500 milliliters is within 5. So what does that mean the volume could be? Well, obviously V minus 500 could equal 5, the positive case, which would give you 505, or minus V minus 500 could equal 5. So that would mean if you solved it, took the negative to the other side, multiplied both sides by negative, V would equal 495. So the min or max would be 495 and 505, and I think we can do that one algebraically like we did, and probably some of us would have just done it by hand. Looking at these now, I want you to determine, fly on your own, what are the answers to these graphically? Pause the recording and come back to see it. So for the first one, you can see they intersect, looks like -3 and 7. The second one looks like the point of intersection happens at an x value of 4. For the third one, looks like it's at an x value of -4 and -4 and +4, and lastly 0 and 4. Ron guessed there were 50 jelly beans in a jar. His guess was 15 jelly beans. His guess was off by 15. What are the possible jelly beans in a jar? Well, obviously 35 or 65. Right, an absolute value equation that could be used. We could have said the absolute value of x minus 50 is got a difference of 15. And that's the end. Please ask any questions that didn't make sense and be ready to talk about restrictions a little bit more tomorrow. Thank you guys. We'll see you tomorrow.